All right. So welcome to another video of CS360, and this time we will cover ambiguity in parse trees and Chomsky normal forms. So we've seen context-free grammars, right? And context-free grammars, you know, are things like this. Whoops. Right, and so one thing you can notice from such a grammar is that oftentimes there's a lot of ambiguity in how you derive a string, right? So you can derive a string, you can derive a string by replacing the start variable with other variables according to rules. So you can pick any rule and kind of apply it here. So we can do this, but there's a lot of options for how to do it. Okay, so here I derived the open bracket, close bracket string. That was one way to do it. But of course, I can do it in other ways. So here you can see that I replaced the second S here with bracket, S bracket, with some rule. And then I replaced the first S with epsilon. I can do the exact same derivation. This is called a derivation, except I'll write the order in which I replace the variables. I'll flip the order. So here I first replaced, before I first replaced the right hand S and then I replace the left hand S, I can just do the reverse. So I can first replace the left hand S with epsilon and I will get S again. And then I can replace the right hand S with bracket S bracket. And then I can replace it with epsilon. And so I get what's essentially the same derivation. I only wrote the sequence in a different order, right? And because each variable, what you replace each variable with does not depend on the other variables in any way. These two derivations are essentially equivalent, even though the sequence of strings is not. So so maybe the best way to think about it is to think of this as a parse tree, what's called a parse tree. So we start with S at the top, and then we kind of write a tree of what we replace S with. So here we replaced S with SS first. That's the first thing we did. And we replaced the left S with epsilon. We deleted it basically. And the second S, we replaced it with bracket, open bracket, S, close brackets, which will just make those three children of this second S. And then we replaced that second S, that final S with epsilon again. So so this object is called the parse tree, the one I'm circling here. Okay. And what a parse tree does is it shows you what happened to each variable. And the parse tree kind of tells you that these two written derivations are really just completely equivalent because they have the same parse tree. So each variable here is replaced, in each derivation is replaced with the same thing. I'm only writing the order in which they're replaced differently. So if I were to draw the parse tree for one of these derivations, then I'll get the same tree. Okay, so that's the sense in which they're equivalent. So parse tree is an important notion, and it's a nice way to think about how a string is derived in a context-free grammar. Okay, and the final string, so if you see a parse tree, the final string, how do you read the final string from such a parse tree? You look at all the leaves from left to right, and you basically concatenate them together. So you take this epsilon, and then you concatenate it with this open bracket, and then with this epsilon, and then with this closed bracket. And so you would get the string epsilon, open bracket, epsilon, closed bracket. But epsilon, of course, just stands for nothing, right? Like it's our way of denoting the empty string. So really, this is open bracket, closed bracket, okay, which we know is really the final string that we get here. Okay, so so this is the notion of a parse tree, and now often when we write on paper, we don't. It's annoying to draw trees. We kind of want to write things in one line more compactly than drawing a tree. And so it's useful to know that a parse tree always uniquely is specified by what's called a leftmost derivation. This is a derivation in which we always substitute the leftmost variable first. Okay, so all the variables in a derivation eventually need to go. They eventually need to be substituted with something. And the order doesn't matter in which we draw the substitution. So we can always choose to do the leftmost one first. And each parse tree uniquely corresponds to a leftmost derivation. So in this case, we can take S and we'll replace S by SS. Then we will replace the leftmost S to get by epsilon to get S. Okay, so we kind of went down this path first to do this S going to epsilon first. And then we see what happened to this right-hand S, and the right-hand S becomes bracket S bracket, and then bracket bracket. So this is actually the second derivation here, is a leftmost derivation. Okay, and the leftmost derivation is unique per parse tree. So it's a kind of a convenient way to denote a parse tree or to specify a parse tree by specifying a leftmost derivation. Okay, so that's a useful concept to know. Now, note that sometimes one string, like this bracket bracket string, can have other derivations. Like we can derive this string just by going like this. So this is a shorter derivation, and it's not at all the same as derivation above, even though it's still a leftmost derivation. So the leftmost variable in each intermediate string here was always the one that's replaced. So you can see that this parse tree will actually be different. Let's draw it over here. The parse tree will look like open bracket S, close bracket, and then epsilon. Okay, and so we have a different parse tree. And there's two different parse trees that correspond to the same string. Okay, so you can see that this can happen in a context-free grammar. So here we had a context-free grammar, and the context-free grammar is called ambiguous if this can happen, if there's some string that has more than one parse tree, or equivalently more than one leftmost derivation. If so, then the whole grammar is called ambiguous. Okay, also the string can also be called ambiguous. The string has more than one parse tree. Now, sometimes we can fix this by switching to a different context-free grammar that generates the same language. Okay, so we can have this context-free grammar that's different from before, but still generates the same language, which goes, let's see, I think it was this. Okay, so this is a different context-free grammar than the one before, but it still generates the language of all strings of balanced brackets. And now the derivations should be unambiguous. So for the open bracket, close bracket string, there should be only one leftmost derivation, which is this, which is S. It gets replaced by bracket S bracket. And then we have to replace the leftmost variable first in a leftmost derivation. So we get this, and then finally we get open bracket, close bracket. So here, this is the only way to generate the string. And in fact, each string has a unique derivation. Each string that can be derived in exactly one way. And the parse tree, let's just draw it. The parse tree that we just denoted with the leftmost derivation. Well, we first made the substitution open bracket S, closed bracket S. Okay, and then this became epsilon and this became epsilon. So this is the parse tree, okay, in this context-free grammar. So remember, a parse tree, you know, a parse tree, to write a parse tree, you need to know your context-free grammar G, and you need to know your string W that you're writing a parse tree for. But even then, the parse tree does not have to be, so the string W, of course, has to be in the language generated. This has to be able to be generated by the grammar. But even then, it's not necessarily unique. For some grammars and some strings, there might be multiple parse trees that are not equivalent for the same string. Okay, but for some grammars, each string does have a unique derivation. Okay, these are the unambiguous context-free grammars. Each string there that is in the language will have a unique derivation. Okay, now you may wonder whether we can always turn a context-free grammar unambiguous in this way. Can we always remove ambiguity by changing the context-free grammar? And the answer is no. So there is so the sort of the standard example showing that the answer is no is for the language A, which is 0 to the I, 1 to the j, 2 to the k, such that I equals j or j equals k. Okay, and then these are all positive integers or non-negative integers. So we can generate this grammar by basically having well, the start variable. We can either generate a string that that looks like that has the same number of zeros and ones, and then any number of twos. Okay, so we can either do that. Let's call that xy. So let's make sure that x gives us the strings with the same numbers of zeros and ones. So x looks like this. Okay, so then x can become any. Basically, this means that x generates 0 to the n, 1 to the n. Okay, so and then we can make y generate. So then y is going to generate like 2 to the m. Okay. So this is what y generates. Or we can sort of do wz here, where w goes to 0, w, or epsilon. So then w is going to generate 0, 0, 0 to the k or whatever. And then z is going to generate 1, z2, or epsilon. So then z generates 1 to the L, 2 to the L. Okay, so it should be clear that this context-free grammar does generate the language A. It's not too hard to see that. Okay, but it does so by basically having two options, one for the I equals j case and one for the j equals k case. Now, if both to generate the string 0 to the n, 1 to the n, 2 to the n for some large n, then it turns out that there will be two paths to do this. One by picking s goes to xy first, and the other by picking s goes to wz. So there'll be two ways to generate the string 0 to the n, 1 to the n, 2 to the n. And it turns out that no context-free grammar can avoid this. Every context-free grammar that generates exactly the language L will have two different parse trees at least for the string 0 to the n, 1 to the n, 2 to the n. Okay, for sufficiently large n, for some sufficiently large n. So this is a fundamentally ambiguous context-free language, in that any context-free grammar that generates this language must be an ambiguous context-free grammar. Okay, so so it is not true that we can always turn a context-free grammar unambiguous. However, what we can do is we can put a context-free grammar into what's called the Chomsky normal form. Okay, so Chomsky normal form is a special form that is going to be quite nice and quite convenient for thinking about context-free grammars in the future. And in Chomsky normal form, all the rules have very, very simple forms. So first of all, one form is x goes to yz, where these are variables, okay, and y and z can also be equal to x. Okay, so this is basically one rule is variable going to two variables, this is one type of rule that's allowed. Okay. Another type of rule that's allowed is basically variable going to alphabet symbol. Okay, so this is another type of rule that's allowed. This is x going to c. And then lastly, we have to deal with, if these were the only allowed rules, then we wouldn't be able to generate the empty string. Okay, so this is a problem because sometimes we want to generate the empty string in a context-free grammar. So we want to be able to generate the empty string, but we also want to minimize the number of times the empty string can occur, because the empty string can kind of create ambiguity if it can occur too many times, right? Like part of the problem with some stupid context-free grammars like this, is that you can keep using stupid rules and then undo it by deleting them, by replacing variables with epsilon. So we sort of want to eliminate ambiguity as much as possible by eliminating epsilon as much as possible, but we can't completely eliminate epsilon because sometimes we want to generate the empty string. So the most we can eliminate epsilon is to only allow the start variable to generate epsilon. Okay, so you only use epsilon when you're creating the empty string itself. Okay, so this is a possible rule. So this is a possible allowed rule where s is the start variable. But then there's the worry that maybe because we have this rule, because s can become epsilon, then maybe s will occur over here on the right hand as y or z. Maybe they will turn into s, and then we can basically secretly have other variables turning into epsilon because of that. So what we're going to do is we're going to ban the start variable from occurring on the right hand side of any rule. So basically s cannot, this is going to be a condition, s cannot occur on right hand side of a rule. Okay, so a grammar that has these properties is called in Chomsky normal form. Okay, so this is called Chomsky after the linguist Chomsky, Noam Chomsky, normal form. Okay, so the idea behind Chomsky normal form is that we kind of clean up the grammar as much as we can. So first of all, we can make sure all the rules only have two variables on the right hand side, just because if you wanted a longer sequence of variables, if you wanted kind of x goes to y, z, w, then we can split this string of three variables up into pieces, right? We can have one variable like x prime that's going to become y, z, right? X prime is going to become y, z. That can be a new rule, and x prime can be a new variable. And then instead of that top rule, we will have x goes to x prime w, and then x prime goes to y, z. Okay, so we can replace this rule on top with the two rules on the bottom, and that's equivalent. So, in that way, we can always assume that one variable only turns into two variables at a time. Okay, and we can also make sure that the alphabet symbols are not mixed in with the variables. And we can completely eliminate epsilons in all circumstances except when the string you're generating is epsilon. Okay, so in particular, every variable except for the start variable cannot turn into epsilon. Okay, so no variable can ever turn into epsilon through any sequence of events except through this one rule that immediately the start variable becomes epsilon and you've generated the empty string. Okay, so then the parse trees, so if you have a grammar in Chomsky normal form, if a grammar G satisfies these properties, then its parse trees either look like this one special parse tree, S to epsilon, which just generates the empty string. That's one possible parse tree, okay, but only for this empty string. Only the empty string has this parse tree. Every other parse tree looks like this. It looks like S, and then you have like XY here for some other variables XY, and then it's basically a binary tree, like maybe a YZ, and then you can replace these with alphabet symbols like so you can have a parse tree Oops. So you can have a parse tree that looks like this maybe when your grammar is in Chomsky normal form, where the variables basically form a binary tree each time a variable splits into two variables, or the variable may terminate and then it doesn't split at all. It just becomes a character, exactly one character. Okay, so if you deleted all the leaves, if you deleted all these characters at the end, you would just get a binary tree of variables. Okay. But the characters at the end where each variable turns into exactly one character, that gives you the final string. So here, the final string would be 0, 1, 0, right? So this is a parse tree for 0, 1, 0 in some kind of context-free grammar that's in Chomsky normal form. I did not write down the grammar, but this would be some parse tree for some grammar that's in Chomsky normal form. Okay, so Chomsky normal form is very convenient, and it turns out that every context-free language has a parse tree, has a grammar that's in Chomsky normal form. So in other words, every context-free grammar can be turned into Chomsky normal form without affecting the language it generates. Okay, so of course, not every context-free grammar is in Chomsky normal form. Some are not. But when you have a context-free grammar that's not in Chomsky normal form, you can convert it to Chomsky normal form without affecting the strings it generates. Okay. And this is very convenient because in Chomsky normal form, we have a very good grasp of what the parse trees look like. Okay, there can still be multiple parse trees per string in the language. It's possible, as we saw before with the string 0 to the n, 1 to the n, 2 to the n in that one language A that we saw previously. So that string, even when you write your grammar in Chomsky normal form, that string for sufficiently large n will have more than one parse tree. However, the parse trees will all have this very nice form that they look like a binary tree, and then everything kind of turns into one character exactly. And there's no epsilons except for this one special case where you're generating the string epsilon. And that will be very convenient, especially later when we try to prove things about context-free languages, like how to prove a language is not context-free and so on. So we will need Chomsky normal form a lot in order to prove such things. Now, the proof that you can convert any grammar into Chomsky normal form is kind of tedious. There's a sketch of it in the notes. It kind of gives an example of how to do it. But it's kind of a long, annoying conversion. Usually you start with some reasonable looking grammar. And then by the time you turn it into Chomsky normal form, like your grammar was, something simple. And then by the time you turn it into Chomsky normal form, it has like 50 variables and a bajillion rules, and it's a big pain. So, it's not a very nice operation turning it into Chomsky normal form, but it's always possible, and that will allow us to prove various things about context-free languages. Okay. So that's it for this lecture.